Okay, in this video, we're going to look at examples that show the application of Watson's lemma. The question wants us to find two-term asymptotic approximation of each integral valid as lambda goes to infinity. So for example number A, we'll start it off here. So this here is our f of t, which we're going to have to need to expand in Maclaurin's. Now the Maclaurin expansion of this one is going to work out exactly the same as the binomial, so whichever way you take. So we are going to adjust the limits to 0 to infinity, so we're going to have, since we're only looking for the two-term approximation, so that means we are only interested in the first two terms of the binomial expansion of square root 1 plus t. So this is going to be the integral from 0 to infinity e to the minus lambda t squared plus t cubed over 2. And then at this point we are going to make the substitution. So we are going to set u to be equal to lambda t, just like we did in the derivation. So if we do that, then this integral is going to be still limits from 0 to infinity. This is going to be e to the minus u. This is going to be u squared over lambda squared plus u cubed over 2 lambda cubed, and then this is going to be du over lambda. Then we are going to integrate this using gamma functions. So the first term is going to give us gamma of 3 divided by lambda cubed. The second term is going to give us gamma of 4 divided by 2 lambda to the power 4. So these are going to be the first two terms, leading terms in the asymptotic approximation of this integral, which we can simplify like that. Okay, so let's go to example number B. So in B we've got the integral from 0 to 3 e to the minus lambda t ln 1 plus t squared divided by square root t. In this case we are going to have to work out the first two terms of the Maclaurin series of ln 1 plus t squared. So this here is our f of t. The main ways of doing this, I'm just going to work this out as follows from the summation of 1 over 1 plus t squared. So first two terms of this will be 1 minus t squared. If we multiply this by 2t, then we are going to have 2t minus 2t cubed, and then plus lots of other terms. If we integrate on both sides of this, then this left hand side is going to be ln 1 plus t squared. The right hand side is going to be t squared minus t to the power 4 over 2 plus lots of other terms, and then plus a constant, so doing an indefinite integral. If we set t equal to 0, then this left hand side is going to be ln 1, the right hand side is going to be k. So that tells us that k is going to be equal to 0. So therefore these will be the first two terms of the Maclaurin series of ln 1 plus t squared. So what that is saying is that we can rewrite our integral as follows. So ln 1 plus t squared here over square root t. So this we can write, we are going to again adjust the integration limits to 0 to infinity. Then here we're going to have t squared minus t to the power 4 over 2, all divided by square root t. And then of course if we simplify, it's going to be integral 0 to infinity t to the power 3/2 minus t to the power it's going to be 7 over 2, and then plus lots of other terms. Then we are going to do the standard substitution. So we are going to set u to be lambda t. Then if we do that, this integral is going to be integral from 0 to infinity. There's going to be u to the power 3 over 2 over lambda to the power 3 over 2, u to the power 7 over 2 over 2 lambda to the power 7 over 2. And then we're going to have du over lambda outside here. Then if we integrate this using your gamma functions, this is going to be gamma of 5/2 divided by lambda to the power 5/2. It's going to be gamma 9/2 divided by 2 lambda to the power 9/2. And then we can actually using your properties of lambda, we can write this as follows. There's going to be 4 here. This is 4 lambda to the power 5/2. Then here we're going to have 1 minus 35 over 4 lambda squared. So that's how we can express the first two terms of the asymptotic approximation of that integral. Then we're going to go to C. So in C we've got the integral from 0 to infinity e to the minus lambda t squared sine t dt. So first thing with this integral is the fact that it's not quite in the your standard Watson's lemma form because of this being t squared. Okay, so what we're going to have to do is we're going to have to deal with that first. So if we let x be t squared, then of course it means t is going to be square root x, and dt is going to be dx over 2 square root x. The integration limits are going to remain exactly the same as before. So our integral is now going to be 0 to infinity e to the minus lambda x. Then this is going to be sine square root x, then dx over 2 root x. This is now in the standard Watson's lemma format, where our variable is x. So we just need to do the Maclaurin's expansion of sine square root x. So that's going to be square root x minus square root x cubed over 3 factorial, and then many other terms. Is divided by square root x. We're going to bring the 1/2 this side. So this is going to be 1/2 integral from 0 to infinity minus lambda x. This is going to be 1 minus x over 6 dx. Then we make another substitution. So this time we're going to set u to be lambda x. So when we do that, this integral is going to become so 1/2 integral from 0 to infinity e to the minus u 1 minus u over 6 lambda du over lambda, and then again applying your gamma functions, this is simply going to become of 1 over lambda minus gamma of 2 over 2 lambda squared, and then of course this is just 1 over lambda minus sorry, that's this is supposed to be 6 here. Okay, so that's going to simplify to 1 over 6 lambda squared. Okay, so that's example number C. Then example number D, integral from lambda to infinity of e to the minus t squared dt. So again, this integral is not quite of the standard lemma, Watson's lemma format, for 2 reasons. First of all is the t squared here, and then the second one is the lower summation limit of lambda. However, we can sort those two by introducing a new variable, t minus lambda. When we do that, then the lower summation limit is going to be 0, and the upper summation limit is still going to be infinity. And then we will see what algebraic manipulations we can do in the function inside the integral. So our integral is now going to be integral from 0 to infinity is going to be e to the minus, so minus t squared is going to be x plus lambda squared. Dx is dt. So let's do, we're going from t to x. This of course is the same as the integral of e to the minus x squared minus 2 lambda x minus lambda squared. Then e to the minus lambda squared is a constant, integral from 0 to infinity. This is going to be minus 2 lambda x, and then e to the minus x squared dx. So this is now like our f of t, if you like. So we can actually do the Maclaurin series expansion of that. So that's going to be 1 minus x squared dx, and then we need to put this in the standard gamma function form. So we are going to make the substitution u equal to lambda x. If we do that, then our integral is going to look as follows. So we're going to have e to the minus lambda squared, integral from 0 to infinity. This is going to be e to the minus u, 1 minus u squared over lambda squared, 4 lambda squared because of that term, 2. This is going to be du over 2 lambda. And then we evaluate this using gamma functions. The final expression is going to be 1 over 2 lambda minus 1 over 4 lambda cubed. So that's going to be the two-term expression, asymptotic expression of this integral. Okay, thank you.